that b squared would be equal to the square of q1n1, q2n2, q3n3, all the way through to qn ni to be squared. So that can be written as, through the laws of exponents, q1, 2n1, q2, 2n2, q3 to the power of 2n3, all the way through to qn to the power of 2ni. Okay? Okay? The important thing here is this, is that irrespective of our choices of a and b, okay, a and b can be written as a product of primes, where the powers associated with each prime is either even or odd. But when we square a and when we square b, okay, the list of primes, the list of primes that occur, all occur in even number of times, So that's important, So clearly, all primes, occur an even number of times, when we square them, Well, what does that mean then for this identity, So let's go back to the identity. So let's consider one again. Let's say consider b squared p is equal to a squared. Now, this is saying that a squared is equal to b squared p. But a squared's factorization, factorization, is a product, of primes, of even power. Each prime occurs an even number of times. Now, p as a prime, p either occurs, in the factorization, of b, or not, or not. It either occurs in the factorization b or not. If it does, occur, it occurs in the factorization in b an even number of times. And then this p times itself, it results in it occurring an odd number of times. Now, that's a contradiction. Don't forget, the factorization of b squared is also a product of primes that occurs an even number of times. If p occurs in that list, well then that means that p occurs an even number of times, and this time here, which means it occurs an odd number of times. But a squared is a product of primes that have even power. So that's a contradiction. What about if p does not occur in the factorization of b? If it doesn't occur in the factorization of b, well then it only occurs once here, which is an odd number of times. And hence, well, a squared is, as I said, is a factorization of primes of even power. So, well, here's a prime that only occurs once. So that's a contradiction as well. So what we have is we have arrived, at a contradiction, and this is because we have assumed, that the square root of p can be written as a rational number. So actually what this implies, so therefore, we have the square root of p where p is prime, is in fact, an irrational number. So there you go. So the main thing that's required here is that a squared and b squared, is a product of primes, but it's a product of primes of even power. So no matter what, a squared must be a product of primes of even power, because it's equal to, because it's a squared, But that's equal to b squared times p. B squared is a product of primes of even power. If p occurs in that list, well then p has resulted in that prime occurring an odd number of times, one more than the even number. If it doesn't occur, well then it only occurs once, which is an odd number. So there's a prime that will occur an odd number of times. But actually a squared by definition has an even number of prime powers, which is a contradiction. So there's a contradiction here in this particular equality, and this particular contradiction has arisen from this particular fact up here. Okay, so what we've actually really shown is that the square root of p cannot be represented as a rational number, and so must be irrational. Okay, guys, and once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And I hope that this video was in some way helpful. Well, I hope it was intuitive, but more importantly, I actually hope that was helpful for you. And thank you for watching. Okay, bye bye.